Dear viewers, today's presentation will speak about the relationship between the dose and the response. This presentation will be the last in the Pharmacokinetics series. The goal of today's presentation are three main goals. First, we have to know what does it mean onset of action and duration of action. Second, we should know what does it mean area under the curve and what are the application of this phenomena. Third, we have to know what does it mean therapeutic dose, blood concentration, and therapeutic index, and how they are calculated. Just if we imagine that I'm taking paracetamol, which is a non-drug used as analgesic to treat headache. Suppose that I follow the blood concentration of paracetamol after taking the drug for a certain period of time. Suppose I follow the blood concentration after 2 hours, 4 hours, مثلا, for example, 8 hours, 16 hours, and so on. Then I plot the relationship between blood concentration of paracetamol and time. What do you think will happen? What we will see? First, we will see a slow rise in the concentration of paracetamol in blood till it reaches maximum. A slow increase in the concentration of paracetamol till it reaches maximum. This increase in paracetamol concentration represents the absorption phase of the pharmacokinetic absorption phase. Once absorption finishes, elimination will start and the level of paracetamol in the blood starts to decrease till it reaches 0. Okay? Of course, this phase will represent the elimination phase of the pharmacokinetic of paracetamol. Okay? Now, the maximum concentration achieved is known as Cmax. And the time that achieves, this is time axis, and the time that achieves Tmax is known as Tmax. Okay? And the time at which Cmax becomes half, 50%, this is known as T-half. Okay? So we have drawn the relationship between blood concentration and time. We see that blood concentration increases by time till we reach maximum concentration. This maximum concentration is known as Cmax. Then elimination starts and the drug will be eliminated by the body, and therefore the concentration in the blood will be decreased till it reaches 0. This is the elimination phase of the drug, and the time at which Cmax becomes half, 50%, this is known as T-half. Okay? Now, the total area in the bell-shaped curve, as you can see, this area is known as area under the curve. Area under the curve. This is a very well known term in pharmacology. Area under the curve, or AUC. What does the area under the curve reflects? What does it reflect? What does it mean from the clinical point of view? It reflects what's known as bioavailability, which is very important expression which we'll hear a lot about in pharmacology. Therefore, area under the curve reflects the bioavailability. Bioavailability is very simply defined as how much of the drug reaches general circulation after administration. How much bioavailability, what does it mean? It means how much of the drug reaches the general circulation after administration. Bioavailability is very important term, as we say later, because it will determine how much of the drug will reach a site of action and can produce action. Therefore, we can say that the larger area under curve, the higher the bioavailability. The higher the bioavailability. This is very important definition. So, what are the applications of the area under the curve? What they are used for clinically? There are many applications, there are many uses. I will concentrate only on 3 applications which are very important in pharmacology. The first application is the comparison of bioavailability between different drugs. Bioavailability between different drugs. Between different drugs. Okay? Different drugs. Just imagine that we have 2 drugs. Drug A and drug B. This is the area under the curve produced by drug A, and this is the area under the curve produced by drug B. Both of them, they are used, for example, treatment of hypertension. 2 drugs A and B. This is the area under the curve for drug B, and this is the area under the curve for drug A. And both drugs, they are used for treatment of hypertension, for example. Which of these 2 produce the higher availability? Which have the larger area under the curve? A, of course. Then we can say that A produced more bioavailability than B. Okay? Yep, this is the first application for the area under the curve, is the comparison between different drugs. 2 drugs, they are used. For example, this is a standard drug of known and this is new drug, for example. Okay? We want to know whether the new drug produces higher bioavailability. We compare it with the standard drug. In this case, we say that the new drug produces lower bioavailability than the standard drug, or it produces higher. It depends on the area under the curve. Yeah, because this is the first application of area under the curve. A second application, important application, is to determine therapeutic dose. Therapeutic dose. Which dose should be used can produce therapeutic effect? As we know, just imagine that I'm taking 100 milligram paracetamol. Okay? And I measure the area under the curve for this 100 milligram. And produce this type of curve. Suppose I increase the dose up to 300 milligram paracetamol. What do you think happened? What do you think will happen? Of course, 300 milligram will produce larger area under the curve. Okay? Now, suppose 100 milligram produce no effect. Suppose that I'm taking paracetamol to relieve headache. I have taken 100 milligram, which produce this area under the curve. But this dose produce no effect. Suppose I increase the dose up to 300 milligram and this produced an effect. It removed the headache. The headache removed. صداع مشي. In this case, this dose produced an action, produced an effect, the dose. So the dose is known as therapeutic dose. Therapeutic dose. Okay? Therefore, not any dose will be therapeutic. Therapeutic dose is the dose that can produce certain concentration in the blood that can end up with an effect. Okay? Okay. Now, the concentration, the maximum concentration, which we call Cmax, which is produced by the therapeutic dose, is known as therapeutic concentration. Therapeutic concentration. Okay? Therefore, we have two new terms, therapeutic dose and therapeutic concentration. Okay? So what's the therapeutic dose? The therapeutic dose is the dose that can produce an action. Therapeutic concentration is the concentration that can achieve a pharmacological effect or an action. Okay? Then, this is the second application of the area under the curve. Let us imagine that instead of 300 milligram paracetamol, I increase the dose to 3000 milligram of paracetamol. Just imagine. Of course, it will produce very high area under the curve. So at the beginning, I started with 100 milligram and there was no effect, no therapeutic effect. I increased the dose up to 300 milligram and this produced an effect. Okay? This, as I increase the dose, the effect will continue till I reach a dose that can produce toxic effect. Toxic effect. Okay? Of course, I don't need the toxic effect. I want the therapeutic effect. Okay? So, what's the difference between the toxic effect and the therapeutic effect? This difference. So, in low dose, the drug produces no action. By increasing the dose, a certain dose can produce therapeutic effect. If I continue increasing the dose, we reach a dose that can produce toxic effect. Okay, the first dose that can produce toxic effect. This toxic effect, dose that produce toxic effect, is known as toxic dose. And the difference between the therapeutic dose and the toxic dose is known as therapeutic index. Therapeutic index. Okay? So what's the therapeutic index? The therapeutic index is the difference between the toxic dose and the therapeutic dose. Okay? Now, suppose the therapeutic index is large, like in this example. In this case, the therapeutic index is 10. About you have to increase the dose of the drug 10 times to reach the toxic dose. Okay? So, what's the use of therapeutic index? What's the use? Therapeutic index, when we say therapeutic index, the larger the therapeutic index, the safer is the drug. And vice versa. Why? Why the larger the therapeutic index, the safer is the drug? Because we have to take several times the therapeutic dose to produce the toxic effect. For example, in this example, I have to take 10 tablets instead of 1 tablet to see a toxic effect. Okay? So, contrary or vice versa, the smaller the therapeutic effect, the smaller therapeutic index, the more toxic is the drug. This is very important application. Okay? So, in a small dose, the drug produces no effect. I've increased the dose, we reach a dose which can produce a therapeutic effect, and this dose is known as therapeutic dose. Okay? This therapeutic dose, if we increase it, the effect will continue, but will reach a dose that can produce toxic effect. This dose is known toxic dose. The difference between the therapeutic dose and the toxic dose is known as therapeutic index. The larger the therapeutic index, the safer is the drug, and vice versa. Okay? Okay. Now, let us take an example. Suppose I have two drugs, drug A and drug B. Drug A have a therapeutic index of 100, while drug B have a therapeutic index of 5. Which is safer? Which is a safer drug? More safe. Which drug is more safe? Drug A or drug B? Drug A, of course. It is more safer. Drug A is more safer. Why? Because I have to increase the dose, therapeutic dose, 100 times before I can get toxic effect. But for drug B, I have to increase the dose only 5 times to get the toxic effect. Okay? So what's the use of therapeutic index? What's the use? The use of therapeutic index, suppose how my drug is used for OTC drugs. OTC means over the counter, means that the drug has not, it can be taken without a prescription or without a drug prescription. In this case, it is commonly used like tablets which are used or capsules which are used for treatment for common diseases like headache, like common cold, like hyperacidity, etc. Many common use of drugs which does not need prescription. They are known as OTCs, over-the-counter drugs. So in this case, these drugs should have very high therapeutic index. They should have large therapeutic index. Why? Because they are commonly used and there is a possibility of mistake that a person will take, for example, 3 or 4 times the dose recommended. So they should have a large therapeutic index so that they don't produce toxicity which can be fatal sometimes. On the other hand, suppose the drug is anti-cancer drug. Anti-cancer. Anti-cancer, as we know, it is used under very close medical supervision. Very close medical supervision. Plus, and that is life-saving. Because cancer, if not treated, it can kill. So in this case, the drug does not have to have a large therapeutic index. In this case, our drug can have a small therapeutic index. Okay? So this is the second application for the area under the curve. The third most important application in the area under the curve is after chronic administration of the drugs. Third application is after chronic drug administration. Suppose I'm taking the drug for acute use, as in case of headache. In this case, I will take only 1 tablet of paracetamol that will produce a therapeutic concentration, and then it will be eliminated, and that's it, finished. But suppose I'm taking a drug for a chronic disease like hypertension, like diabetes mellitus, any chronic use. In this case, we need to keep the drug in high concentration in the blood for a longer period of time. Okay? Suppose now I'm taking the drug. Once I take the drug, blood concentration will rise. This is the concentration against time. This concentration will rise till Cmax, then it starts to decrease again. Once it starts to decrease again, I have to repeat the dose. Repeat the dose. I have to take the dose to keep the blood level at the therapeutic concentration. Okay? This is all doses. I have to repeat the dose to keep the blood concentration at the therapeutic level. This is known as steady state concentration. Steady state concentration, or CSS, steady state concentration. Okay? So in chronic disease, I have to take the drug several times a day in order to keep the blood at therapeutic blood, to keep the drug at therapeutic blood level at a steady state concentration. This steady state concentration is determined by the area under the curve. There is a very famous example equation which they use to calculate the steady state concentration, okay, which equals the area under the curve divided by t, time. Okay. The frequency of the repeated administration, this frequency of the repeated administration will depend on the half-life time of the drug. Frequency of administration. Is the drug going to be taken once a day or twice a day or 3 times a day to keep the steady state concentration? This depends on the half-life time of the drug. Of course, the longer the half-life time, the less is the frequency of administration. Longer T-half معناها means less frequency of dosing. Okay. Usually to reach steady state concentration, in the plasma, it needs about from 4 to 5 times T-half. Okay? So once I take the drug, to reach a steady state concentration, needs from 4 to 5 times T-half. For example, suppose the T-half of the drug is 4 hours. For example, T-half is 4 hours. In this case, I need from 16 to 20 hours before drug can reach steady state concentration. Okay, this is general rule. Always take from 4 to 5 T-halves before we reach a steady state therapeutic concentration. This applies for all types of drugs. But sometimes I need a faster steady state concentration, especially when the drug half-life is very long. Faster steady state concentration, especially with long T-half. Some drugs, they have very long T-half. In that case, it will take many days to reach a steady state concentration. So what they do in this case, they give what's known as a load dose. They give a high dose, maybe 5 times, 6 times the normal therapeutic dose to boost the concentration of the drug in the body, in the plasma, and to reach steady state concentration fast. Maybe instead of 10 to 12 days, it might take 1 or 2 days. This is very famous loading dose. Famous examples of digitalis. digitalis preparation, which is used for treatment of heart failure. It has very long T-half, and therefore usually it is given in a low dose to produce quick, steady state concentration. So this is the major application of area under the curve. And by this we have finished talking about the principles of pharmacokinetics. In summary, what we have discussed today, we talked about onset, and in summarize what we have talked about today. We talked about the dose response relationship, and we said what is onset and what's duration of action. We talked about the area under the curve and its application. The application we talked about is the comparison between different drugs. Second application is to a determination of the therapeutic dose and therapeutic index. Third is the determination of steady state concentration in cases of chronic administration of drugs. I hope that you have enjoyed this presentation. That, as I have said in the beginning, it will be the last in the pharmacokinetic series. I will be more than happy to receive your comments and feedbacks by writing your comments. Please don't forget to like the presentation and subscribe to my channel. May Allah bless you all. Keep in health and tranquility. Wassalamu alaikum wa rahmatullahi wa barakatuh.